Welcome to our pitch video on micro underwater vehicle hydrobatics. Let us first give you some insights on our underlying research project. Our goal is to monitor environmental fields such as temperature fields or chemical distributions in confined tanks, which can be found widely in the process engineering industry. As taking measurements is usually too dangerous for humans, we want to do this with a swarm of micro-autonomous underwater vehicles. For this task we designed the micro underwater vehicle HippoCampus. It's about 35 centimeters long and thus small and agile enough to operate in confined tanks. Here you see the vehicle driving around our test tank in Hamburg, which is about 4 times 2 meters and 1.5 meters deep. As you can imagine from these movements you see here, you need a robust attitude controller to take care of the vehicle dynamics. Our work mainly consists of 3 parts. The first part is a new vehicle design. Several iterations brought us to a 3D printed modular design which greatly simplifies maintenance. For instance, we can quickly exchange the broken motors as you can see here in the drawing, and also we can adapt the vehicle to a different task by changing its length. The second part is an attitude and depth controller for micro underwater vehicles. Geometric controller which compute the attitude error and SO3 are widely used in the aerial drone community. We adapt this control scheme for the underwater domain and integrate it in the HippoCampus control architecture, which is based on the PX4 firmware stack. The third part of our work is the Submerged Rotational Pendulum, also called Furuta Pendulum. We use the pendulum as a benchmark problem to demonstrate the performance of our proposed control scheme. The pendulum is actuated with rotations around the roll axis of the HippoCampus Micro AUV. Therefore, we design a pendulum controller which can apply moments on the roll axis of the vehicle. We conduct experiments to demonstrate and examine the performance of our vehicle and its control architecture. Hereby we put a special focus on the robustness and on how the controller interact with each other. The control task is first to keep the vehicle in an upright pose and second to swing up and stabilize the pendulum. Due to the high water damping, the swing up phase includes a downward motion of the vehicle. We apply external disturbances to the vehicle and to the pendulum to demonstrate the robustness of the proposed control scheme. It can be observed that the controller recovers quickly from large attitude deviations, which shows the robustness of the proposed scheme. Finally, we want to mention that our complete project is open source. You can find the vehicle design, the firmware and detailed manuals on our project webpage. We are looking forward to meet you at ICRA.